Record on this computer? Okay, cool. Hopefully that doesn't, uh, I can figure out how to access it later, but yes, there we go. It should be recording now. All right, well, it's up to you guys then. What questions do you guys have about any topic, maybe pick a homework problem or pick something. I don't really have anything structured here. Problem 42 from Eric. Okay, what is from Eric? Do you have like a link to that real quick? Okay. Let's take a look. Problem 42, page 52. Okay, got it. Let's take a look. So we are doing problem. This is one of the practice problems in the midterm. Okay, got it. So problem 42 from Eric. A string W of parentheses of regular parentheses and brackets is balanced if it satisfies one of the following conditions. Either W is the empty string, W is equal to the parentheses surrounding X for some balanced string X. W is equal to brackets surrounding some balanced string X, or W is equal to XY for some balanced strings X and Y. For example, this string is balanced because we have a bunch of those, and yeah, so on and so on. Okay. So design and analyze an algorithm to determine whether a given string of parentheses and brackets is balanced. Then for B, describe and analyze an algorithm to compute the length of a longest balanced subsequence of a given string of parentheses and brackets. Describe and analyze an algorithm to compute the length of a shortest balanced supersequence. And design and analyze an algorithm to compute the minimum edit distance to form a balanced string of parentheses. Oh, wow, there is a lot of this. Yeah, so I'm just going to answer any of the questions, one by one that you guys have. Yeah, A, B, C, D should be not that bad. So E, okay, E, F, G, to compute the longest common balanced subsequence of two given strings of parentheses and brackets. Okay, so this, let's just start doing this. Let me see if I can bring that screen back. So what was it, like 42, Eric, part E. So we want to find the longest common subsequence. So balanced subsequence of strings balanced balanced X and Y. Okay, so you see longest common balanced subsequence, you immediately should think no, X and Y not necessarily balanced, so just of strings X and Y. So you should immediately think that, oh, we might be able to solve this using DP, right? And my initial thought is, okay, so what exactly makes a think about, like, we think about the properties of what a string might look like if it's balanced, and how we might construct a balanced string if given nothing. Okay. So let's see here. In general, if we can create a balanced string if the closing bracket is the exact same as, so let me think about this. We can form a balanced subsequence if I actually haven't looked at this yet, so give me like a minute or two to think about it. But if anyone has any kind of ideas, then also um, feel free to just like chime in as well.
Where do I find this question? Hello?
Yes, that should be from that book. Um, so longest common balanced subsequence of two given strings with parentheses and brackets. So obviously my initial thought is to build off the longest common subsequence algorithm, although I'm not sure that that may work in this case because, or just like blindly applying would work because we have to make sure that the common subsequence is balanced as well. Um, although there is a way I think that we can do it. It's a little bit weird because I don't know if, so analyzing the runtime of this algorithm is going to be a little tricky just because um, the way I'm thinking it, because so the way to, if we go back to A, right? If obviously like the general algorithm to figure out whether a given string of parentheses or brackets is unbalanced, it should be pretty easy to implement um, just by using like a something like a stack where you just keep the most recent kind of like opening parentheses with bracket on top of the stack, and every single time you find a closing one, just make sure that it is like when you pop it off, it's you know it works as well. So my initial thought here is to, instead of so use DP in this case and make sure that whenever it kind of like adapt the longest common subsequence algorithm, except have an additional DP state also keeping kind of track of the state of like the stack. If we were to also keep track of some longest common subsequence. So you might say that for the original longest common subsequence, maybe longest common subsequence, we might index x with index I and y with index j or something like that. And what we might do then is also keep an additional variable. This is what I'm thinking of, at least. Keeping track of some stack of opening and closing parentheses and saying that, oh, we can form using the prefix and x string x, just using prefix I, and string y using prefix j. like that, we can form, a a current state, I guess, something like this. And that's essentially what I'm assuming, because then the transitions become kind of similar, right? If we, if the next characters match, like for example, this character like at index I and this character at index j, they match, and if it's an opening parentheses, and we might be able to update the state of this in order to kind of, I guess, fit so if both of these characters were like an opening parentheses, we might update this to be something like this, where we just append this on. And if it were like a closing parentheses, then we might, or if this were like instead like a closing bracket, we would just check to make sure that it matches this last one, just kind of like how we would check like if a normal normal string is balanced or not. So, and then just take it off. If this were like a closing parentheses, then it wouldn't match and we wouldn't be able to, take this one off. And that's my initial thought for doing it. I'm not exactly sure if this, because we're kind of keeping like a stack, like kind of like a state, like this state is really, really huge, right? Because it could potentially go up to, length I or so. And not only that, there's two types of opening. So there might be 2 to the I states, or well, I guess 2 to the n states here. So there might be some way to optimize this, which I'm not thinking about right now, or there's some way to like optimally think about the runtime that I'm also not thinking of right now. But this is kind of like the first idea that I'm getting for solving this problem. I'm sorry if you already figured that out, or if this isn't like rigorous enough, but maybe I think this idea might be worth to look into. And no, I believe you should be able to like do similar things for F and G, or sorry, for F at least. Well, for F, it might actually be a bit simpler because what I'm thinking about is like, again, you might be able to adapt like the longest palindrome algorithm that you learned in class into this exact sort of thing, using kind of like the same ideas of sort of keeping some state here. But unfortunately, I'm not exactly sure if this would 100% work or not. But that's just my kind of like initial thoughts here. I hope that helps. Yeah, unfortunately, I'm not exactly sure, or I might need a little bit more time, but to think about this a little bit further. But yeah. Okay. Looks like there was another question about doing question 2 of homework 2's multiple choice question. I don't know if I have that pulled up right now, but let me see if I can find it. Do you know if it's on Brightspace or not? Because I'm not really in charge of like managing the homeworks or anything, so I'm actually not sure where to find this type of stuff.
A screenshot, it's on Gradescope. Hello, can you hear me?
Let me see if I can find it on Brightspace, or is it on Gradescope actually?
It's on Gradescope.
Oh shoot, my mic is sorry, my I wasn't able to hear you. No, my bad. I turned on my speakers now. You can hear
Can
it
you
now.
hear me now?
Yeah, I can hear you now. My bad. Holy crap.
Yeah, it's on. Yeah,
Okay, summation of 1 over 4 over I from 1 to n. Okay. So homework 2. Um, so summation of 1.4 over I from I equals 1 to n. Okay, let me search that up real quick on Gradescope just to make sure that I'm able to find things correctly. Yeah, that's what I was thinking, right? Because it should be the harmonic series. But let me just take a look just to make sure. Yeah, just relaying the problem. So are they asking for like the exact value of it? Because if so, yes, it should just be like just straight up O of log n, because we can just pull out 1.4 here.
yeah.
And we should have shown in class. There's a cool way to do it with a with an integral actually, but this is actually big theta of log n.
How do you get big data of log n here? Can you show me how you get it?
Okay, so there's an interesting way of actually doing with an integral here. Because if you think about this is, I guess you don't need to know exactly how this works for the midterm, but just know that this is big theta of log n. But I'll show you here, like a quick overview here. Because if we show this graphically here, this is 1, this is 2, this is 3, 4, and pretend we're like graphing out along the curve of, so this has height of log 1, or sorry, 1 over 1, my bad, 1 over 1. This here has height 1 over 2. This here has height 1 over 3, and so on. We can, if we draw the integral like this, okay, well, we can show that actually what the summation is doing is summing up these rectangles. Okay. And actually, if you take like the sum of the rectangles, I'm not going to go through this rigorously and do everything, but the sum of the rectangles, the sum of the rectangles is approximately equal to, integral from 1 to n of 1 over I. And if you just do a little bit of calculus, then that should just get you that this is approximately log n. And there's more rigorous ways of showing that this is true, but this is just like a very brief outline. Yeah.
So usually if you see anything like, summation of fractions, then you could, it most likely is log basically. Like if it was log 1 of 2 plus 1 of 4 plus 1 of 8.
Okay, so this is specifically for the harmonic series, right? So if it was 1 over 2 plus 1 over 4 plus 1 over 8 plus da da da, well, this actually converges to 1, just using like a slightly separate argument. But yeah, there's because you might think about this as if we take like a square, 1 over 2 is 1/2 of the square, then 1/4 is half of that remaining area, 1/8 is half of the remaining area, and each new number only adds half the remaining area, so it converges to the the size of the full square. And the harmonic series is just like a special case. For like multiplicative factors like this, you would want to use like the geometric series formulas, which I'm sure you should be aware of, which is the
Uh-huh.
first element uh, over the ratio.
Oh, I get this. Yeah, I can search these up online.
Yeah.
Yeah.
Okay. So hopefully that cleared up some of that stuff. Okay. Then for that, and then that should just be that. Someone asks, can you help talk about how to convert the problems into SAT? Okay, so this is kind of like a general question that gets asked like over and over and over again. I'm guessing like, oh, how do I know if a problem is polynomial time, and how do I know if a problem is NP hard? And I mean, kind of like the general answer is just you just kind of at some point it just kind of becomes intuition as to which one it is. But in general, if a problem kind of seems difficult to do, then you might like, I know this is like a really terrible answer for like actually kind of having like a very concrete way of doing things, but in general, like if you look at a problem and it seems like no matter how you wrap your try to like wrap it around DP or wrap it around any of like the methods we've done in class, there has always is some like exponential factor. There's likely to be, it's probably like NP hard and there's a reductionist stat. And in order to do that, I mean, we have like, I believe on the midterm review, or on the midterm, actually on the midterm sheets, there should be just like straight up like a list of a bunch of like NP hard problems that we know are reducible to SAT. And so if you take any of the problems that on the midterm and kind of like compare them to any of those problems, and they seem kind of similar, you might know, oh, this is probably reducible to that problem, and we can just say that, oh, it's trivially reducible to the satisfiability afterwards. And I mean, that's basically as much advice as I can give, because kind of actually like determining this type of stuff is kind of like an art almost at a certain point. But and I'm sure you've seen some of the reductions in class where we go into like really really crazy stuff, and we're definitely not expecting you to do that on your own. All the questions on the midterm, if they if they kind of look, and they're designed to look similar to some of um, the problems that we've like some of the NP hard prompts that we've already given you. So maybe like I believe that you should just be able to use that kind of like as an like kind of as a guide to solve some of these problems. Okay.
Where, where do we find those NP hard problems again?
If you, I believe, if you look on Piazza,
Yeah, I
we,
tried looking at that though, and then what and then where?
I think the midterm one rules and guidelines.
Yes.
Um, if you look on, there should be a PDF attached, and on pages 2 to 3, there's like a bunch of NP complete problems that we've just. Oh no, yeah, on the next page too. So three pages of NP hard problems that, or NP complete problems that you can compare to. Um, and of course, most of them are going to be the ones that we've covered in class, but there's always this large guide that we can look at as well. And this will be given to you like on the midterm as well. So you don't need to go and memorize all of this. But yeah, okay, yeah, thanks, Akshay. Yeah. Okay, so if we go back to homeworks, or our questions here. So do you guys have like a central location where you're given the multiple choice questions, or are they on Brightspace or something? Because I'm not 100% aware of where to find all of them, or if you guys can like relay them to me. Oh, just on Gradescope. Wait, let me see if I can take a look then. Ah, okay, yeah, I see it now. Okay, thank you. So let's go to homework 3. multiple choice Q6. Let's take a look. Q6. Okay, so consider the following recursive algorithm for exploring a directed graph with n vertices and m edges. So for each edge, leaving, okay, so starting at V, for each edge leaving V, if E is unmarked, then mark E and edge search on W, which is the neighboring node. So pick the smallest upper bound on edge search from the following, which are listed in increasing order. Okay. Let me think about this real quick. So this means that for each edge leaving V, we're going to mark it. Then we're going to search on every single edge afterwards. So this means that each edge is only each edge is searched exactly once, but the recursion makes things a little interesting here. So it's a directed graph with n vertices and m edges. So I think probably for something like this, the best way to think about this is to like think about what the worst case scenario would be. And let me see. Oh, okay. So for I think the main idea here is that um every single time we call edge search on a node, what happens is that no matter whether like we don't ever mark the node. So it means that it's possible for us to visit the same node more than once. And no matter what, we're always going to iterate through the through all the edges, to check if they're marked or not. So for every single time we visit the node, we're going to have to kind of iterate through all of its here. Let me kind of like just draw what I'm thinking here. So this would be homework 3 multiple choice question 6, I believe. So suppose we have a node and it has a bunch of edges leading in and it has a bunch of edges leading out. Okay. So what this algorithm is doing is, every single time we call it on a node, we kind of iterate through all of its outgoing edges. And, if it's not marked, then we go through, mark it, and call it on whatever, da da da. But the important part isn't that we're like the recursion here. It's the important part that even though we mark each edge, so that each edge here, like for example, once it's marked, we're not going to traverse it more than once. When we like suppose even if we've marked all of the outgoing edges of a node first, if like we find another another edge leading into here, we're still going to have to kind of like iterate through all of these edges just to make sure they're marked again, because we don't do anything with the node itself. So so kind of like in the worst case scenario, we'd visit each we'd visit each node like O of m times, and every single time we visit so so okay, so let's think about like kind of like the worst case scenario. How many how many incoming edges can a single node have, right? How many incoming edges? So this is on the factor of O of n, because it's a directed graph and there's only so many nodes that exist in the graph. So even if we draw like an incoming edge from every other node to this node, there's only ever going to be incoming O of n. And this also means that regardless of this, like the worst case, how many outgoing edges there are, we can, draw one to each other. So there's also, O of n worst case. But it seems here that the answer is O of m times n, which is probably because I'm missing something here. Because even though I think it has to do with like the m times n has to do with the recursion part. But I'm trying to pin down that thought right now, because from what it seems currently, it seems to be O of n squared, which leads me to believe that the second answer, but that's not correct. Let me think. Oh, okay, I see. And this analysis is done for every node. So there's an additional O of n factor actually here. But that makes me think it's O of n cubed, which is also not correct because that's too far up. But I think because we're only considering edges here, so we're only considering edges here. These two, instead of counting them as O of n, these should be counted as O of m. And so getting we finally get this for every node, and that should give you O of m times n. It's a little tricky, I think. And if I had more time, I'd like think about this more and formalize this thought process a bit more. But hopefully that should kind of like, because I mean O of m, sorry, the number of edges is like bounded by O of n squared anyways, right? And this is like, again, the worst case scenario when we can bound this by like a lower bound all the time, because we only ever process so for every edge, it only ever comes out of one node and enters one node. So this is like done 2m times, and at the worst case. But then we should get something like this. Okay, then let me see homework 4. Problem 4. Let me go back and take a look. So homework for multiple choice questions. Let's take a look at the questions and homework or problem 4. So whenever we run DFS on a directed graph, every directed edge u to v has its starting point u in an earlier layer or the same layer as its endpoint v. And this is false. So this is because, we might say that, so let's just say we run BFS and we're just going to like draw out the layers. So this is like layer 0. There's a bunch of edges, that lead directly from 0, get you to layer 1, a bunch of directed edges lead you to layer 2, and so on, right? But the thing is, this doesn't say that, this does not say, in the BFS tree. It doesn't say in the BFS tree. Right? This is asking about any directed edge. And any directed edge, well, this like, some, node in the second layer can still have like a directed edge backwards to, layer 0. But, this just doesn't get included in the search, right? Because, oops. Yeah, so this just doesn't get included in the search because well, I mean, this is already an earlier layer and we're only ever searching on to like later layers, right? But it's so in the BFS tree, yes, sure, it's possible that there is it's impossible for a directed edge to go from a later layer to an earlier layer, but like in the total graph, but it's still possible. Like the edge can still exist, it's just that we're not really considering it. That's the idea here. Okay, then since we've already covered homework 3, multiple choice question 6, let's take a look at then homework 1, multiple choice 6. I'm sorry that it's taking me a little bit to like go back and forth between everything, but Gradescope is kind of annoying at loading everything. So question 6. Okay. So consider the following special case of Boolean satisfiability that we will call k variable Boolean satisfiability. Let k in n be a fixed parameter, so e.g. k equals 42. In k variable Boolean satisfiability, you are given a Boolean formula with exactly k variables. And decide whether this has a polynomial time algorithm or polynomial time implies a polynomial time algorithm for general satisfiability. And this question should just be that it has a polynomial time algorithm. So it has polynomial time algorithm. And the important thing to note is this is because k is fixed. We know the value of k beforehand. Okay. So this means that what we can do is just say, okay, so if we're given, k variables, all we have to do is to basically brute force it, right? We just have to try every single combination of variables and say, oh, is, there's, 2 to the k different ways to assign a Boolean value to every variable, but we can try it all because, if, k is equal to 42, if it's fixed, then, this becomes, we try all 2 to the 42 combinations and look at that, that's a constant. Okay, so because this is a constant, we could just say, oh, then we just go through all the clauses, plug it in, check if every one is satisfiable in some way or another. And then if there is one out of these 2 to the 42 different combinations, then we can say, oh, that's it, it's satisfiable. And if there aren't, then oh, it's not satisfiable. And this might seem a little confusing, but again, important part is k is fixed. The reason that in general, satisfiability is, does not have a polynomial time solution because we don't know what the value of k is. We're just given like a bunch of, clauses. It can be any number of clauses. And, if we have, like n clauses, then we can have up to, 3n Boolean variables. And then, looking at 2 to the 3n, well, that's definitely not, not constant. So in general, when you see like k is fixed or something, that should like immediately like bring up like red like alarm bells saying, okay, there's something going on here where we can substitute this fixed value into an equation and make something that looks exponential to be actually linear.
How did you get 2 over here, like 2 to the 42 over here? How did you get 2 over here?
Yeah. So here, let's just say we have like variables x1, x2, da da da, all the way up to x, 42, right? So for the first variable, we can assign it, true or false.
Oh, I get that. Yeah,
Yeah.
that's how you get 2 or
Yeah.
40.
So each one, there's like two options, right? So it's like 2 times 2 all the way down. That's 2 to the 42.
Yeah, yeah, 2 to the 42.
Yeah.
So how do you know it's here? It's like polynomial, it's like a polynomial time algorithm here.
Right. Because then all we have to do, suppose we're given like some assignment, right? Let me move this down so this doesn't like interfere. But like suppose we're given that x1 is equal to true, x2 is equal to true, x3 is like false or something, and so on. We can take this and we have some like x1 or x2 or not x3 or something like this, and all we have to do is to take these values and like kind of like just plug them in and see, oh, is it satisfiable? Well, true or true or true, and oh, this clause is satisfiable. This works, and you do this with every single clause, given like some assignment. X42 is equal to false. Plug in these variables and see whether that satisfies or not. And going through that and plugging in all the variables is, obviously polynomial time. We're just checking, one clause at a time. And so if we do this, for every single assignment, and assuming that the number of assignments, again, because k is fixed, is constant, then we can say, oh, this problem can be done in polynomial time in total. Okay. So that should cover that. If I can scroll here and go down. If I'm not missing anyone, then it should be homework 4, multiple choice, question 5. And let me pull that up real quick. So homework 4, MCQ. MCQ 5. So consider the problem of deciding whether a directed graph G contains a walk with at least k edges for an input parameter k. Okay, so this does have a polynomial time solution, which is a bit weird considering that, sometimes you might have heard that finding a path of size k is actually NP complete. But the reason that finding a walk is polynomial time solvable is because in a walk, we can repeat vertices and edges. So in a path is defined as, we have like some like kind of like graph here. In a graph, like a path, can't, come back to the same vertex more than once, right? So if we like go back here, that's no longer considered a path. Or if we traverse the same edge more than once, that's no longer a path. But in a walk, we don't have that restriction. A walk is just, a sequence of moves. So the reason that this a walk has a polynomial time solution is because so first off, observation. If there's a cycle in the graph, in the directed graph, then we can make infinite length walks, right? And this should be pretty obvious because even if we have a cycle of length 3, right? We could just take this and just go, oh, okay, go to node 1, then 2, then 3, then back to 1, 2, 3, and so on forever. Okay. So if there is a cycle in the graph, we can make a walk of any length. And this means that, oh, this is not a cycle, actually. I drew this the wrong way. There we go. So if there's a cycle, infinite length walks, so the answer is always, true. Yes, there is a walk of length. Okay. Okay. Now then, this means that the only interesting case of this problem then is if the graph has no cycles. So if no cycles, okay, if no cycles, this means that we know the graph has a DAG. And well, what problem do we know that we can solve on DAGs really easily using DP? Well, we can solve this using longest walk on a DAG. Okay. So because if we solve for the longest walk on a DAG, or not even longest walk because there's no cycles, we can just call this the longest path on a DAG. A walk is only distinct from a path if it repeats vertices, but you can't ever repeat vertices if it's a DAG since all the nodes are moving in one direction. So if we have a longest, so we can solve using longest path on a DAG here, and there's a DP solution that I believe all of you should have covered. But the idea is that if the longest path is of great, like if the longest path has length greater than k, then that path satisfies that works. And if the longest path has length less than k, then we say, then if the longest path has length less than k, then there's no path that could ever reach length k. So then it doesn't work. But that still does give you a quick solution for the problem. Okay, cool. And then let's move on to multiple choice question 2 then.
So quick question.
Yes, quick question.
How do we know this is not a polynomial time, the walk?
How do we know it's polynomial time?
Yeah, or not?
So you mean like longest path on a DAG?
Yes.
This should be, I think you guys covered this in class, right? There's a DP solution after you topologically sort it. But I guess I can just cover it here like real quick. Just suppose we have a bunch of edges topological sorted like this, like that, or something like this. Then the longest path, let's just call it LP, longest path, even though LP has different meanings. The longest path at a vertex V is 1 plus the maximum of all edges, or sorry, all vertices, overall vertices U, such that there's an edge U to V of the longest path at U. So we traverse one edge, and so every single time we traverse one edge, and the longest path increases by 1 depending on which one is the maximum previous node. But this is like a typical DP solution that I believe you guys covered in class, so I'm not going to worry too much about it.
And so we can say this time is in like polynomial time, this DP solution.
Yeah, so this is like known polynomial. So this is polytime. And of course, above here, cycle detection is also polytime, as covered in class.
Okay.
So both steps are in polynomial time. Okay. Then let's take a look at multiple choice question 2 real quick. Okay, so 2 has a few parts to it. So use recursion trees to analyze the following recurrence. Okay. So T is equal to something plus n. And then T1 is some constant value that we're not going to worry about. Let's see here. We have Tn is equal to O of n for what values of A and B, where A and B are tight as possible. Okay. Let me see. So I'm not sure what way you guys learned in class. But this just seems like it's just looking at it makes me look, it looks like it's linear time here. Just because if we suppose T of n is O of n, then substituting it in, we find that this is approximately n over 2 plus n over 3 plus n, and this goes out to like less than 2n, and that, I mean, it's not a very rigorous way of proving it again, but I also haven't done recursion trees in a while, and I also don't know like how you guys exactly did it in class, but I guess this is the way that I would do it at this point after not doing recursion trees for like a year or so. I'm sorry if that's not a very good answer here. Okay, so looks like I've reached the bottom of chat here. So if anyone else has like any other like questions that they'd like to cover of any sort, I mean, it doesn't have to be okay. Homework for general guideline and reduction. Okay, so I don't. Oh, so okay, so if it's so first off, I believe this would be multiple choice question 3, not question 3, because I don't think homework 4 is due yet. You don't want me to do your homework for you, right? But I'll again go over like kind of like the general guideline on reductions.
What I meant, the multiple choice question.
Yeah, the multiple choice question. But again, kind of, so we're on, I don't know if you were here earlier when I was talking about this, but you're on the midterm, you're going to be given like a giant list of NP complete problems. And you can kind of just like, I guess the best way to do it is just compare them to each other. Like, if you have a problem that you think might be NP hard, just go through the list and compare all of the problems and say, oh, do these two look similar? And again, we're not here to like kind of trick you or make you like prove a reduction that's like really difficult. All of the question are designed kind of for you that are already designed to sort of be similar to one of the ones already seen. And so all you have to do is to just say, okay, so do any of these look similar? If they do look similar, is there a way to transform the input of of this problem to a different one of these problems, and so on and so on. But that's basically generally how you do it on the test. Okay, then yeah, sorry if that's not super useful, but again, reductions are more of an art than a science at a certain point, so it becomes kind of hard to give like general overarching advice without being too vague, I guess. Okay, so let's take a look again at then homework for multiple choice question 3. So considering the following problem, so given a strongly connected and directed graph, the goal is to compute the minimum length circuit that visits at least half the vertices. Yes, and I'll do that afterwards. So a walk that starts and ends at the same vertex that visits at least half the vertices. Okay. We know that the entire graph is strongly connected, right? This means that every node can visit every other node. So this walk is at least always going to exist, but the goal is to compute the minimum length vertex, minimum length circuit that visits at least half the vertices. Let me think. So again, this is one of those times where kind of like the ideas of reductions come into play, because I'm looking at this problem and I'm trying to, apply DP to it, apply some structure to the problem using directed graph, trying to, reduce it to a DAG or do something like that. But it's just like on first glance, it doesn't seem very possible to do it. So immediately I'm thinking, okay, what if this problem is indeed actually strongly what if this problem is at least indeed like NP hard? But let me try to formalize this then.
So if we know a problem is NP hard, does it mean it implies a polynomial time for SAT?
Yes, in general, it's NP complete, or yeah. So NP hard means that it's at least as hard as any other problem in NP. I don't know. Did you guys like formally cover what the definition of NP was in class? If not, then this like notation I'm using might be a little bit confusing. At some point, yes. Okay, yeah. So if it's NP hard, then it's at least as hard as any other NP problem in NP. And in general, NP hard and NP complete are equivalent. Well, I guess not exactly, because NP complete means it's in NP and it's NP hard, but that's beside the point. Yes, in general, if there's like if you can find like a link to any of the problems in the handout, or not in the handout, I guess in this like you can reduce any of the NP complete problems listed in like the front matter of the test to any of one of the questions, then yes, we can consider that that's equivalent to having SAT being reducible to it, and so on and so on. But yes, the answer is yes. I spoke for too much. Either way, let's take a look at this again. So the minimum length circuit that visits at least half the vertices. Let's see. So my initial thought is, what if we can reduce Hamiltonian circuit to this problem? So as a quick reminder, Hamiltonian circuit is, finding a path that visits every single vertex, and returns to the same vertex at the end of the path, or at least there's an edge. So because this problem does look very similar, and so now I'm thinking, okay, so how do I manage to transform a Hamiltonian circuit into an instance of this problem? Well, what I'm thinking then is something like this. Give me a second. So suppose we have a solution for this problem. Suppose, we have some black box that solves, I don't know what this problem should be called, but like min half circuit. Min half circuit. Suppose we have some black box that solves this problem. And I think then that means we can take this the Hamiltonian, we can take the Hamiltonian path problem, Hamiltonian circuit, transform the input and have this black box be able to solve it if and only if. Okay. So I'm thinking is, so we're given some graph here, okay, and we're asked the Hamiltonian circuit is asking if we can find some circuit that visits every single node, and this problem is asking if there is some circuit that visits half the nodes, the minimum length. So what I'm thinking then is, so note that if a Hamiltonian circuit exists in this graph, then the graph is guaranteed to be strongly connected. So okay, so we don't need to worry about this section because we can just give it some strongly connected graph. Then suppose we kind of like have this graph here, okay, and this is like maybe the circuit in the graph, kind of messy, I don't know. What we might be able to do is say that there's n vertices, n nodes in this graph. What we might also do is then create like a bunch of auxiliary nodes like this. Oop. So a bunch of also n extra nodes. Okay, and then just take like an arbitrary vertex here and say, okay, and connect all the nodes, back and forth with that one vertex. So let's think about what this does. So now we have a graph with two n nodes, okay? And we know that now this graph has to be strongly connected. So because all we're doing is we take this like big circuit that's already strongly connected, and we're adding a bunch of nodes, but we're adding return paths for each of these nodes. So these will be strongly connected as well. So the entire thing is strongly connected. Now we have two n nodes here. Okay. And this original circuit is going to take up exactly n nodes of the graph. And what's n over 2n, so that's 1/2, right? So now think about any path that includes any of these extra nodes. So any circuit that includes any of these extra nodes here. So let's just say that we find some path in the graph, or sorry, some other circuit in the graph. And at some point we go to that extra node and back, because that's the only connection. What we can always do is say, okay, let's just take these two nodes and just take them out. This will 100%, 100% reduce the number of edges in this graph, or reduce path length, right? No matter what. Now, because this will reduce the path length, this means that our black box of finding the minimum circuit that visits 1/2 nodes or more, well, it's going to always never include these edges, this path, these edges. No, this doesn't actually work then, because it's possible that we might need to take a longer circuit within here to visit a different node. Let's use a slightly different formulation then. What we're going to do then is, instead of connecting all of these to one node like this, what we're going to do is, connect them in kind of like a cycle like that. I think this is going to work a little bit better, because now if we include any of these extra edges, if we have to include any of the extra edges, we kind of have to go through the entire cycle before doing that. And then I think that should be sufficient to say, okay, this cycle of length n, it's not going to be any worse than if we traversed, to another node inside the original graph. So I think this formulation should work out. So now we've note that this graph is still strongly connected, and we can just say, okay, go away. This can never occur, because we can always visit other nodes in here with better accuracy. And I think no, this also doesn't work, because the worst case scenario here, my bad, is that the worst case scenario here is that we actually get we just return just this, because actually this circuit already just satisfies it, because this is exactly a cycle of length n plus 1 actually. So instead of adding n extra nodes, okay, let's edit the solution one more time. We add n minus 2 extra nodes. N minus 2 extra nodes. Okay, now this cycle is of length n minus 1. So just this cycle isn't going to affect like the solution at all. So now we can just say, okay, this goes away, and then saying, okay, so now we can finally say that no, the minimum circuit here can't include any of the extra nodes. Okay, that was a little bit of a trip, but most reductions are kind of a trip where you kind of mess around with a bit. But this should finally give us, okay, so then the circuit that's provided to us by our black box algorithm here should be the exact same circuit as maybe like the circuit that we might get in our original graph. So it's the exact same as like some circuit we get in our original graph. And this means that, okay, then all we have to do is to compare, right? So if the length of circuit is equal to exactly n, then we know that there's a Hamiltonian circuit, because a Hamiltonian circuit visits all the nodes, doesn't repeat edges, and covers all the nodes. And then we have ham circuit. Okay. And if the length of the circuit is greater than n, then this means that if there was a Hamiltonian circuit, well, then we would be able to find this path, or this exact circuit of length n. But there's no circuit of length n, so we have to just say that, okay, this is bad. And there's no Hamiltonian circuit. So we can finally link these two problems. Okay, we take this black box, solve the problem, do some checks, then we can say with certainty if there's a solution to Hamiltonian circuit or not. Okay, this means that if there's this black box works in polytime, then Hamiltonian circuit, all we're doing here is adding n minus 2 extra nodes. The Hamiltonian circuit has a polytime, but we're given that this is one of these NP hard problems. So that means, if we reduce it up, that means SAT has polytime. And that's it. So this has no polynomial time solution that we know of, or if it does, then it implies a solution for SAT. So again, hopefully maybe solving this problem might give you like a little bit more insight into how at least I might solve some of these problems, or how I might tackle some of these questions, where you kind of just like look at the problem and try to like think of a few ways. DP doesn't work because this isn't a DAG, because it's strongly connected. Trying to do like BFS or something, pathfinding doesn't necessarily work because we're trying to find longest, or not even like it's like a circuit. Circuits are kind of weird, So it's like, some like our typical algorithms like shortest path or something isn't really going to work, and like visits half the nodes. That's also like quite like a weird restriction here, right? So then because of that, I'm looking at this and saying, okay, instead of looking for like a polynomial time solution, maybe I can take a look at one of these, maybe I could take a look at one of like the NP hard problems or NP complete problems and find a reduction. And what looks very similar to circuits? Oh, just Hamiltonian circuit. And then, from that, try to look for some sort of, way I can transform the input and then, get this sort of reduction going on. All right. So then let's just move on then to homework 2, multiple choice question 3. And let me pull that up real quick. Was this homework question, multiple question 3? Or was this a different homework? Oh, this is homework 4. Okay, let's go over homework 2 then. Okay, so use recursion trees to analyze the following recurrence. So I don't know if you guys have you guys like learned master theorem at all in class? Like, does the master theorem ring a bell or not? No, and we're not allowed to use it. Oh, okay, I see. Okay, so this one's like a little bit easier to analyze because it doesn't require two separate, I guess, what is it called? Recursions. But once you learn the master theorem, this becomes a little bit easier. But the point being is that, at the top level, we do 2n work, right? Because we're given that much. And we recurse down, 4 times with our children, with a parameter n over 5. So there's 4 children, and each of them are doing n over 5 times 2 work, so 2n over 5. So this gives us like 8n over 5. Each of these children, go down, 4 times, blah, blah, blah. And so we have 16 times, and at that point we've done n over 5 2 times, so it's like 2 times n over 25, I think. That should give you like 32 n over, what is it called, n over 25. And at this point, okay, let's see if we can find a pattern. 2, 8 over 5, 32 n over 25. Okay, so this just looks like the summation of 2n times 4/5 to the I or whatever, and summation from I equals 0 to like infinity. But geometric series, we can just pull out the 2n, so this is equal to 2n times this geometric series, and this we know that it's constant because the fact this ratio is under 1. So it should be all of that. And that should be enough. All right. Any other questions about homeworks or, oh, right. There was something up above I missed, I think. From Eric. So Eric, problem 22 on page 43. Let me take a look at that. Scroll up. So let's define a summary of two strings A and B to be a concatenation of substrings of the following form. So the triangle, so red indicates a substring of only the first string A. Oh, this is a different link. Oh, crap. Okay. Oop. My bad. So different link, problem 22, page 43. Got it. I just assumed it was the same link, but clearly that was not right. Okay. Got it. Okay, so a domino then is a 1x2 rectangle divided into two squares, each of which is labeled with an integer. In a legal arrangement of dominoes, the dominoes are lined up end to end so that numbers on adjacent ends match. So is that the problem you're looking at? Yeah, okay. So 22, A, B, and C. So given an arbitrary bag D of dominoes, is there a legal arrangement of all the dominoes in D? Given an arbitrary bag D of dominoes, is there a legal arrangement of dominoes from D in which every integer between 1 and n appears exactly twice? And given an arbitrary bag D of dominoes, what is the largest number of dominoes we can take from D to make a legal arrangement? Okay. So for A, let's think about this. Legal arrangement of all the dominoes in D. Let's see here. I'm thinking that this can just be solved using kind of like a greedy solution, because okay, I on adjacent, I don't know if this is requiring us to form like a loop or not, like in the example here. Okay, so in the example here, the ends match, but so like the 3 on one and the 3 on the other end matches, but I don't think that's like necessary here, I don't think. So I'm just going to assume that it doesn't really matter, but given an arbitrary bag D of dominoes, is there a legal arrangement of all the dominoes in D? All we can do is, so for A, there should just be a greedy solution. So suppose we have, like a domino here, and assuming that this end we're like not using, we can just like, say if this is a 5, we could just take any domino of like 5 and just like slap it on, I think. And there might be some like some restrictions that you might put on it to make it a bit simpler, like for example, you know so note that every single time you match a domino here, this appears twice. So you like kind of go through the list like 1 2 3 4 5 da da da, and check if there's an even number of that tile in all of them. And because we're like working through like a giant matching like this, where every two have to be the same essentially, there can only be ever two numbers maximum that have like an odd a number of matches, basically, because of like the one lone half on one end and the one lone half on the other end. Every single other has like a pair in between. Every single other number has a pair in between. So first off, if we see like, oh, this is like there's an odd number of ones and an odd number of twos and an odd number of threes, we know there's no way to match all the dominoes. If there's an odd number of ones, then we know that, oh, then one has to be on like one of the ends, and we can just keep matching onwards and just making sure that like two is on the other end. If there's just an odd number of ones, then it's impossible because there has to be some loner on the other half. And if there's no odd number at all, then the two numbers and the ends just have to be the same. Either way, there should just be like a greedy solution where you keep like this like parity argument in mind and make sure that the odd numbers end up on the ends. And because we have like an even number for each of the other ones, no matter what domino we place down, there's always going to be some matching domino later on with that exact number. And so I'm assuming that there's just like, I haven't formalized it, but there should be a polytime solution to just kind of match it. Maybe not greedily, but match it so that the numbers work out essentially. For the second part though, given an arbitrary bag D of dominoes, is there a legal arrangement of dominoes from D in which every integer between 1 and n appears exactly twice? Okay, so let's think about what we might do here then. So note that matching two dominoes together is almost like, if you think about it, almost kind of like a graph, right? So if we make a graph where every node is like a number from 1 to n. So 1, 2, 3, 4, and so on. We can label the nodes to n. If there's a domino of then, that has like 1 and 3, for example, we might say, oh, there's like an edge between 1 and 3, because we can like kind of link them together using this domino. If there's another domino that has 3 and 4, you might draw an edge between the two, and then so on. You might draw a bunch of edges, and this forms some sort of graph. So then let's go back to our question and ask us exactly what is the question asking of us? Well, the question's asking if there's some arrangement of dominoes where each domino appears twice, or sorry, each number from 1 to n appears twice. How would this look? How would this arrangement look in our graph? Well, this means that every single node has two edges, right? Because so this is like, if we can consider any like arrangement of dominoes like a path. Sorry, I should have explained that earlier. So if we put these two dominoes next to each other like this, right, what we can say then is that, oh, this is basically equivalent to like a path from 1 to 3 and then 3 to 4 and then so on. Okay, so then if we want each number from 1 to n to appear twice, what this is essentially saying is that, okay, so every single time we match a domino, the number already appears twice. So once we get to it, we use a number, we can't use it again. And furthermore, our first number here, right, is like kind of like just alone here. And the only way to just include just one more 1 in this case, is at the end where we've done matching dominoes. At the very end here, we have another 1. Okay. So again, how does this appear on our graph? Well, this is essentially saying, okay, this is a path that visits every single node, right? We use every single number exactly once, and it returns, so maybe it returns back to our first number. And this is essentially saying, oh, then does this graph have a Hamiltonian cycle? And we know NP, the whole NP complete thing. So yes, this problem is so So a poly time solution for this problem, then the domino question, B, implies poly time for SAT. And I'm just glossing kind of over the reduction because it shouldn't be too difficult to understand at this point. Okay. Then, given an arbitrary bag D of dominoes, what is the largest number of dominoes we can take from D to make a legal arrangement? Okay. Let's think about this. The largest number of dominoes we can take from D to make a legal arrangement. Let's see here. I think then this problem actually might be NP hard. I'm not 100% certain, but in general, like we have, we might need to update our version of the graph because in this version of the graph I had above, I implicitly assume that we can only use every edge once, right? Because once you use an edge, you can't place that domino, like even like, if you had like 2, 1, 3 dominoes here, we can't place it down again because it would violate, 3 or 1 or whatever. But here here we can, in our new arrangement, it's possible for, like multiple edges to exist like that, between 2 edges. If there's like multiple dominoes in a, that might be able to be matched or something like this. And then this is essentially asking like, what's the longest path? Right? And this, path here, I guess, means that now we can repeat vertices because obviously in order to traverse all the edges, we have to repeat vertices, but we can't repeat edges. So repeat vertices, no repeat edges. And following these constraints, what's the longest path? Well, longest path on a graph is NP hard, NP complete. And it's a little bit weird then, though, because I believe for it to be like specifically NP complete, the graph has to be simple. Right? Simple graph meaning there's only one edge between any 2 vertices. So I'm not exactly sure if this applies here. I'd have to do a little bit more research, but this just seems as if, we just take longest path and apply it directly here. Although this question does have a little heart next to it, which means that there's probably something I'm missing that might actually make it easier to do, but I'm not exactly sure, unfortunately. Because if we were to apply like DP to this problem, it would be a bit weird considering we need to keep track of which dominoes we've used already. And there's 2 to the n subsets of any set of things, and that might get a little hairy. So again, but then again, you see 2 at the end and just kind of think, okay, this is probably NP hard. That's the kind of like the kind of thought process I'm going through here. So just off first glance, this does seem to be NP hard, SAT reduces to it. But this exact argument might not apply like if there's like some sort of weird condition that, or this special condition of repeating vertices and multiple edges doesn't actually apply here, but that's my thought process. Yeah.
How would we know this problem is NP hard or complete?
Longest path in a graph. That's just that is NP hard because you can reduce Hamiltonian path to it.
Oh, so Hamiltonian path was an algorithm that's polynomial, right?
So well, if longest path was polynomial time, then we can find an algorithm for Hamiltonian path that's long polynomial time. And then then we can find actually actually we were actually we were actually given here that number 19 on the midterm front page that the longest path is NP complete here.
So yes. So how did be NP complete the longest path?
Yeah, so it should be NP complete.
Okay.
Because it's given to you.
Okay. So basically tomorrow on the exam we're given those NP completes and then we need to try from that, like hinting with what we're given to see whether identify them as NP hard or polynomial time.
Yeah, essentially.
Okay.
Yep. But yeah, that should be these problems. Yeah, not super rigorous. I might be wrong here, but this looks mostly right to me, so I'm just gonna go with this. Okay. We have some more questions here. So homework 2, MCQ 4 and 5. So did we already cover these earlier? So homework 2. Okay, I guess. Okay, no, we didn't. So yeah, okay. Homework 2, MCQ 4. Let's go and take a look. Homework 2, MCQ 4. So consider the following problem we call the min-max interval sum problem. The input consists of a sequence of numbers and an integer k. The goal is to partition the number into k sub-intervals that minimizes the maximum sum over all the intervals. Okay. And okay, sure. So this problem is nice because we're not talking about subsequences or subintervals is not too bad. And there should be a polynomial time solution for this problem. But what you should notice here is that suppose we have like a bunch of numbers 1, 5, 2, 3, 7, 2, whatever. And we're given like a target number. So let's just say we're given, k is equal to like 10 or something. So we need to make sure that, the sum of all the numbers in the intervals is less than or equal to k. Well, all we can do is kind of just like iterate through and, try to find subintervals that, are less than or equal to k. So for example, 1 has to be in a subinterval. 1 plus 5 is 6. 6 plus 2 is 8. 8 plus 3 is 11, which is greater than 10. So we count this as a subinterval. 3 plus 7, is 10. And 2, or k is not a good number because k is number of intervals, my bad. Let's just say sum is 10, S is 10. Okay. And we see that this is possible to be done in exactly uh three. So here K here is actually 3. And what you might actually think of doing then is actually doing some sort of like a I guess a DP then. So what you might think about doing then is, so if we take a look at each position, saying, okay, so given that, so what is, so let's just say DP at index I is asking the question, given that the last interval we formed ends at index I, what's the minimum? What's the minimum sum, or what's the minimum number of intervals formed so far? And this shouldn't be like too bad to think about how you might create this DP. Just kind of like starting at this number, working back until so like for example, working your way back and checking. So DPI is equal to, so we're forming one extra interval here, plus the minimum number of intervals over some index j is less than I, such that the the sum of all numbers from I to j is less than the current sum, and we take dpj. So this dp isn't like too bad to think about, and we can run this dp if we're given an s. So all we have to do is look at dp n to find the minimum number of intervals that we need for any given sum, and then maybe just like binary search over s to see basically if it takes greater than k intervals to form it, then the sum is going to be too small. We need to like expand our intervals here in order to, or sorry, we need to like reduce the number of intervals, and this essentially means that yeah this essentially means that if we find like that it's less than shit, I'm gonna re-explain this then. If the dpn is greater than k, that means we're using more than k intervals in order to, like the minimum number is going to be more than k, which means that we need to increase our sum here. So in order to reduce the number of intervals, if we find that dpn is less than k, then we can reduce the sum a little bit and say, okay, we might be able to form intervals with a slightly less sum, and we might just then be able to binary search on S to find like the minimum such number. And it's a little bit weird, I admit, but if anyone, if this wasn't clear to anyone, feel free to ask any questions. But essentially, this does give us like essentially maybe like an n squared for the DP and log n for the binary search.
So we're trying to
that's the
find,
following time.
so we're trying to find like k intervals that minimizes the sum of the intervals here
Yeah.
into, and to do that we use dynamic programming to minimize the sum of k intervals, any k intervals.
Yeah. So we're kind of like flipping the problem on its head here, where if we have kind of like a sum here, a given sum that we're like if we're given a sum, we can calculate the number of intervals kind of easily. So that's like the problem flipped on its head, but we can just use binary search on this kind of like reverse problem in order to find a polynomial time solution for the original one. But either way, this is doable in polynomial time. And so we have a polynomial time solution.
Then I'd like to do 2 point question 5 in the same homework.
Yeah. I'm getting to that. So homework 2, MCQ 5.
Yeah.
So consider the problem that we call the min-max sum problem. The input consists of a sequence of numbers, and the goal is to partition into k sets such that that minimizes the maximum sum over all the sets. And so again, as I mentioned earlier, that this problem is going to be like slightly harder now because again, subintervals are like really easy to deal with because, you know, they have to be contiguous. But sets or, you know, subsequences, they're a little bit harder to deal with because you can kind of like pick from any point. You can pick from any point in the original sequence. So this problem gets harder, and it actually gets hard enough that it does become NP complete, because it turns out that subset we can actually reduce the problem subset sum or the partition problem. I don't know which one you guys covered, but subset sum of partition can be reduced to this problem. And it shouldn't be like too difficult to see because partition essentially asks us if we can divide, you know, we have some sequence of numbers here, you know, some sequence of numbers, and we're asked if we can divide them into two sets of equal size or equal sum. So the sum of this set is equal to the sum in this set. Okay. And, you know, you might immediately see some similarities here where you might see that, you know, oh, if we have this sequence and we're saying, okay, let's divide into two sets. So k equals two sets. What does this tell us? Well, let's just say that we have a black box that solves this, you know, I don't know what to call this problem, like a k min max sum problem. Sure.
What's the difference between sets and intervals?
Yeah, give me a sec.
Hello?
So yeah, so a set, you know, so an interval has to be some contiguous segment. So an interval has, all the numbers in an interval have to be next to each other, like this. Okay, so intervals.
But in a set?
But in a set, we can like kind of like pick from anywhere. So you might say, oh, these numbers at these locations, you know, are part of set one. And then, you know, at a different location, we might say the other ones are, you know, are part of set two and so on.
Okay.
Okay. So again, intervals are really, really easy to deal with because, you know, the numbers all have to be next to each other and we get some like really nice ordering properties here. But for sets, they're less easy to deal with because we can pick from anywhere essentially. But again, let's go back here. If we divide into k equals two sets, if we see that this black box algorithm, you know, gives us some, let's just say n over 2, exactly n over 2, that means there's some way of dividing this into two sets such that, you know, one of the sets is actually not n over 2, sorry, sum over 2, where we take sum to be the sum of all numbers here. So if this black box algorithm gives us that the minimum would be s like the sum over 2, then that means that, you know, one set has to have exactly, you know, s over 2, And the other set has to have exactly s over 2 as well. And so if that's possible, if this gives us s over 2, then we know that partition must be correct as well, because there's some way of dividing into two sets such that one of them has some s over 2, the other one has some s over 2. Okay. Now, if this gives us a number greater than s over 2, when does this occur? So this occurs when, we're splitting this into two sets. One has, one has, let's just say some a, I don't know, and the other has some s minus a. So either, because we can't form exactly s over 2, either a or s minus a has to be some like this value, b that's greater, b that's greater than s over 2. And essentially, this just means that this is impossible to form, a set of size s over 2, which means this is impossible for these two sets to have equal size, and and so on, so on. And so its partition must be impossible here. So these two problems, are equivalent. They can, there's a reduction between them. And of course, partition is NP complete. So this just means that we can form a polynomial time solution for SAT.
So, I mean, no, I think the answer for 5 is basically like, a polynomial time implies a polynomial time for SAT. So how is it not like the polynomial time, but just the polynomial time for SAT again?
Yeah, it's not polynomial time, because if there were so if this black box here has a polytime solution, then partition here has a polytime solution. I mean, SAT here has a polytime solution. Then, if this doesn't, that's just essentially what it is.
So basically the partition and the box is a polytime solution.
It does not have, so we do not know, at least, of a polynomial time solution to solve it. If there is a polynomial time solution for this problem, then there has to be a polynomial time solution for SAT.
But for like partitioning and the sets, like we don't know if there's a polynomial time.
Yeah. Essentially, this problem is hard, basically.
So in the last problem, we knew for sure there was a polynomial time, but this time we don't know.
That's correct.
Okay.
Yeah. This problem is difficult. Okay. Then I think we probably have enough time for just one more problem here. Then let's see here. So homework 3, multiple choice question 2. And let me pull that up real quick. So let's see here. And of course, recursion trees. Okay, let's take a look then. Use recursion trees to analyze the following recurrence. We have, okay, so let's see here. So T of n is equal to 5 times T of n over 4 times 2n. If that's correct. Yeah, okay. What does this tell us? So if T of 1 is equal to, and of course, T of 1 is equal to some arbitrary value here. Let's take a look. So 2n, this splits into like 5 children, each with n over 4. So we have 5 children. How much work is this do? Times n over 4. So 2 times n over 4. And this splits into more children, right? Each one has 5 children, so now we have 25 children times 2 times n over 4 twice, so 16. And let's stop, take a look at the pattern, right? So this has so bad at writing summation symbols, but this should have, I from 1 or 0, I guess, to whatever of 2n times 5/4 to the I. Okay, so this is going to be more than what is it called? Because this, I guess this question, this factor here, this ratio here is greater than 1. We can't just reduce it as we did earlier and say, oh, it's a constant time, right? So now what we have to consider is, okay, so what's the height of the recursion tree? And then we can do some analysis on this. So the height of the recursion tree is, we're doing n/4, so it would be, log base 4 of n, right? And because after that many iterations, then we take our our n equals 1 base case. Okay. And then let's see here. Oh man, it's been a while. We can try to analyze this recursion, or sorry, this summation here. So we can take 2 to the n out, 2 to the n out, and say that, okay, the rest of it is going to be log base 4 of n, I from I equals 0, 5 to the 4th here. And let's see here. So this means that this will be, how do you analyze this again? Oh, right, using, like, again, geometric series. So this would be approximately equal to, 5 to the 4th. If I remember this correctly. No, so yeah, it'd be 5 to the 4th. Or no, because it starts at 0. So it'd be 1 minus, 5 to the 4th log 4 and something like this, over minus 1/4, something like this. And if we try to simplify this term right here, we should get that it's approximately like n to the what? Am I just bad? Is it like log base 5 of 4 over, it's like, this is approximately 2n plus n to like the log base 4 of 5. No, log base 5 of 4. No. Log base 4 of 5 over minus 1, something like this. I can't believe I'm this bad at math. Yeah, that's that. Okay. This does seem to be correct. Okay. Then then we just say that, okay, then this will be, this linear term and this here does cancel out, and this would be approximately O to the n of log base 4 over 5. There we go. That took a bit of math, and once you learn master theorem, it's going to be a little bit easier to analyze. But I believe this is a solution to this problem. And oh crap, I guess earlier on there was a problem where someone wanted to go over the un-American path problem. Oh yeah, right here. So let's just do that real quick before time runs out here. So un-American law. So an un-American walk is just any walk that in the walk there is no sequence of red, white, blue, or white, blue, red, or blue, red, white. Okay, so there's none of these. One thing you should notice is that the naming is a little bit tricky because the un-American walk is not the complement of the American walk problem. So what this means is that if some walk in the graph is not an un-American walk, it does not necessarily mean that it is un-American. So for example, a walk with only going through red edges, and at the very end, we hit red, white, blue. This walk is clearly not American because this sequence here says oh, this doesn't follow the pattern. But it's also not un-American because this pattern at the end follows this pattern. Okay, so what's really tricky about this problem is that you kind of have to read it carefully and have to realize that we can't just invert the American walk problem and get the answer for this. And the American walk problem, of course, we covered in PSO. So yeah. Now, this means, but there is kind of like another kind of way to think about this. So we can still apply the concepts that we covered in PSO to this problem. So all we have to note is that whenever we reach like a red white pattern, so the last two nodes, a red edge reached to this node, a white edge reached to this node, this next node just can't be blue, right? It can't be blue. That's all that it's saying. And kind of same here. If the last two edges traversed were white and blue, the next edge can't be red. And we can say this for the third pattern as well, but I'm not just going to say it here. Okay, so the idea then is to split every single node. Instead of like in the American walk problem, we split into 3 nodes, we split into 6. We split each node into not 6, into 9 nodes. Okay, and each node kind of represents the last 2 edges that we traverse to get to that node. Okay, so we split each node into 9. One of them is going to be red, red. Oh, the last 2 edges traversed were red. Then the last 2 edges we traversed are red and blue. The last 2 edges we traversed red, white. And we might say this for every single here. Okay. And every single time we'd like draw an edge between 2 nodes, maybe like there's one node here, like this is red, this is a red edge, then we would just update it saying, okay, so if this was the last 2 nodes visited here were blue, white. Actually, no, we can't say it's blue, white because that would follow the pattern. If the last 2 nodes visited were white, white, then this would lead us to say, okay, so in the last node here, this was white, then this leads into a white, red node. And we would just draw all of these paths, or all of the edges in the exact same way as we did before, except with the restriction that there is never going to be a blue edge leading out of a red white node, right? Because again, that would break this pattern here. There is never going to be like say a red node leading, or sorry, a red edge, not node. I keep saying node. There's going to be no red edge leading ever out of a white blue. But every single other combination, other than these 3 exceptions, we draw edges in the exact same way. And then all you have to do is to, BFS the graph or do Dijkstra's or do whatever your favorite shortest path finding algorithm is, and find the path from S to T that's un-American. And that's the homework solution. Note that actually quite a lot of you guys got an answer to this problem with only 6 nodes, and that's correct because
some of these are some of like the nodes are like functionally equivalent, but this 9 node, like splitting into 9 nodes versus splitting into 6 nodes, like I mean, I think this solution is easier to understand and gives like a better understanding of what this problem is trying to do. Yeah.
So what does it mean we split into node like red, 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 blue, red, W? What does it mean we split it into?
Yeah.
Like, do we split
So
it into edges?
yeah, so it like in our original graph, we have like a bunch of nodes. Our graph might look like this, right? But in our transform, we can transform each graph by taking each node and kind of like splitting it. Okay, so each of these has 9 nodes, and each of these, like this, right? And there's like connections between the nodes, like depending on what the colors are or whatever. And just the edges that we create are going to, et cetera, are going to enforce that the un-American walk property is going to be satisfied. Okay. And this is, again, similar to the American walk problem, but note that it's a little bit more complicated, and of course, it's not exactly the same.
So where do you get WB, WR from? Like, where was the W, where's the R?
Right, because if we're at like these labels kind of represent the last 2 edges we took to get to a node. So at this node, if this node is labeled white, white, what it means is that the last 2 edges that were traversed were white and then white. And then if we traversed a red edge here, we say, okay, this goes into another node, but now the last 2 edges traversed to get to this node are white, from before, and also red.
Okay.
And so we can, by removing certain edges from this graph here, we can enforce this property of the un-American walk, and we should be able to solve it pretty simply.
Okay.
Okay. And unfortunately, I think that's enough time for today, though. But yes, I will upload these notes along with the video. So yeah, thank you all for coming, and hope this helped.
Where will we find the video of this again if we want to use it?
I'm going to see if I can upload this on either Brightspace or Piazza, whichever is going to be easiest for us.
Okay.
I'll take a look. Yeah, no problem.